Now that we've had our discussion on kinetic energy, the natural progression is to start talking about potential energy. What is potential energy? Potential energy is the energy an object has as a result of its position or its state. Okay? It is stored energy, which just means that it's able to do work when released. Okay? By this definition, potential energy is converted to a new form that can do work. Okay? And this is a variety of things. Potential energy can be converted into heat, can be converted into kinetic energy, as we saw in our little skateboarder on the last slides. But there are several types of potential energy we'll be discussing: elastic, chemical, nuclear, and gravitational. Okay, these are all important pieces that we need to make sure we remember. Elastic potential energy. Okay, elastic objects return to its original form when their shape is changed. As you've probably already done to somebody, is if you take an elastic and you shoot it across the room, you're extending the elastic out of its natural state, and when you release it, it's taking that energy and putting it in the form of kinetic energy to return to its original shape. Okay, so energy is released when they return back to that original state. So let's take a look at a spring to remind us about what this is all about. So here we're back into our little diagram. We'll open this up and we'll see exactly what happens. Okay, we'll look at applied force, spring force, displacement, okay, values. Okay, so again, when we start taking a look at this, okay, let's look at the energy. Here we go. Way better. So what we're going to take a look at is this is the displacement away from, you can see along the bottom axis is the displacement away from its original position. Right now it's in its initial position. So if we take and we take the end of this, you can see as we extend it, its potential energy is increasing. It's going up that graph until we reach its maximum position. Okay? And again, when we bring it back, we can see it goes back to its neutral spot. Okay? No potential energy. And again, when we compress it, we see the potential energy increase again. And you can see the potential energy bar graph on the left side of this little diagram. Goes down to 0 and then climbs right back up. So again, if we were to take a look at this in slow motion, we were to compress this spring, when we released it, all that energy would be turned into kinetic energy. Okay, so let's head back to our other presentation. Okay, so again, that is a prime example is springs that we've just talked about, bungee cords, trampolines. The reason why we have so much fun in there is because we're using that elastic potential energy. Chemical potential energy. Okay, energy is released when bonds form between atoms. Okay, and again, this kind of goes back to our chemistry section, but fossil fuels have a high amount of chemical potential energy, which is released as heat when it burns. When you think about your car running, okay, as the fossil fuels continue to burn in the engine, your engine heats up. Okay, that is a direct result of heat being released and breaking those bonds in the fossil fuel. Okay, the source of chemical potential energy for life is photosynthesis. It's taking the sun's solar energy and storing it in the form of glucose. Okay, now I know you're probably looking at the screen like this. You're all confused, have no idea what's going on, weird look on your face. But let's take a look at a picture. Way easier to understand. Okay, when we see an example like this, we have a chemical bond forming at the top part of this little example up here. Okay, now what we're going to end up seeing, okay, when energy is brought in and breaks this bond apart, we see energy released into the surroundings. Okay, just like you see on the diagram. So now we have our two products that are separated. We'll call it 1 and 2. And now we have a whole bunch of free energy floating around. Okay, so once the bonds break, energy is released. However, in order to, as the bond breaks, the potential energy comes out. Spontaneous bonds will then form. Okay, so when they break apart, now they're going to pair up. Okay, we're going to see interactions happen here. Okay, now in order for bonds to form, okay, energy needs to go into the bond. So we lose some of that energy, but not all of it, as you can already see here. We see some of the energy that's still kicking around. Okay, this is the result of a chemical potential energy. When the bonds break, they give off a little bit of energy after they reform this bond. Okay, so again, it takes us back to chemistry a little bit, but an interesting concept nonetheless. Now, nuclear potential energy. Okay, nuclear. Okay, very large nuclei, for instance, uranium, plutonium, there's tons of examples, can be split into smaller nuclei and generate huge amounts of energy. I'm going to underline this several times. Okay? The missing mass that is lost in this is converted to energy. According to Einstein's theory, E equals mc squared, as you've probably already heard. Okay, this is what we call nuclear fission. And this diagram shows us a good example of this. We see the uranium nucleus start here. Okay, we can see as the neutron gets added in, we see it kind of bubble up all weird and start to split. Okay? And then when it eventually splits, these two guys go in separate directions and kick out a whole bunch of neutrons and energy. Okay, so we see a whole bunch of energy float off into the sunset. Okay, now this usually, the reason why nuclear fission is so scary is because these separate little compounds here that go off into the sunset usually cause a chain reaction. So they split into two. And then these guys split into two. And the chain reaction just keeps carrying forward and forward. That's what makes nuclear physics a little bit dangerous, is the fact that it just continues to happen. So we need to figure out a way to control that. Okay? So nuclear potential energy is huge, and it's a very active area of research. So when we start talking about gravitational potential energy, okay, when we look at gravitational potential energy, we see, so when we talk gravitational potential energy, we see all objects of a mass exert a gravitational pull, which you can already see. That's why we stay on the Earth. Okay, it's a very weak force unless the object is massive. As you already know, we're smaller than the Earth, so the Earth's gravitational pull is significantly more than what we give. Okay? However, we can look at the potential energy of the gravitational potential energy an object has through this formula. Okay, so when we're looking at gravitational potential energy, it is measured again in joules. Same thing as kinetic energy. Okay, we have a mass, okay, which is in kilograms again. Okay, the height is in meters. Okay, and most importantly, we have a gravitational pull constant. Okay, this is a constant. This number is not going to change. So this is something that you're going to need to memorize. Okay, 9.81 meters per second squared is what the G value is in this equation. Okay, so important thing to remember for these upcoming calculations. Okay, however, one thing we have to remember is since the gravitational potential energy is dependent on the height of an object, okay, this can change the amount of potential energy an object has if it is changing height. Okay, so what we call this is we say that Eg is relative. Okay, now you're probably thinking, whoa, crazy talk, relative, absolutely hard to visualize. So let's take a look at a picture. Okay, all this means is that gravitational potential energy is relative. Relative. Okay, so if we take a look at this diagram down here, we have a ball sitting on the top of a staircase with 50 joules. Okay, now at the very bottom of the staircase, if this is the ground, okay, we're assuming ground is 0. So at the top up here with the potential energy, we're assuming that it has 50 joules of potential energy relative to the ground. Okay? So it's relative to the ground. So if we go down the staircase, we know that there's 1, 2, 3, 4, 5 stairs. Okay? We would assume each one of these would decrease by 10. Okay? So, however, if we were to look at this potential energy at the top relative to the first stair, okay, we would only see the potential energy as 10 joules. Okay, so it really depends what you're looking at here. If you're looking from the first stair, you have this potential energy. If you're looking down to the ground, you have this potential energy. So it really depends on what you're looking at and what you're relating it to. Okay, so again, if we went down from this spot down to the second step, we'd say that it has 20 joules. Okay, so it's all dependent on how high it is and what it's relative to. So let's look at some examples. Let's do some calculations together. We have a hailstone with a mass of 36 grams formed in a cloud 2.2 kilometers high. How much gravitational potential energy does the hailstone have? So, two important pieces of information. Okay, we have a mass, okay, which is 36 grams. We have a height, which is 2.2 kilometers. We don't like kilometers in this case. We have to convert this over. Okay, so we're just going to go put kilometers on the bottom, meters on top. We know there's 1,000 meters per 1 kilometer. Gives us 2,200 meters. Okay, now we know the gravitational constant, 9.81 meters per second squared. Okay, now we have everything we need to find Eg, our potential energy, because that's what we were looking at in the question. Okay, so Eg, we just plug into the formula and solve. mgh. Okay, so we have our 36 grams. Okay, oh, sorry about that. We'd be given 36 grams. We'd have to convert that over as well. So again, we can, since we're going from grams to kilograms, we move the decimal over 3 spots this way. So it's 0.036 kilograms. Okay, now we're ready to plug in. So we have 0.036 kilograms times 9.81 times our height of 2,200 meters. Okay, so now we come to an answer of 776.952 joules. Now, we have 2 significant digits here limiting us, so we'd have to cut this off at, we'd say 7.8 times 10 to the 2 joules. Okay? 7.8 times 10 to the 2 joules is what our answer to this question would be. Okay? Next question. Let's give it a try. How high would a 3,000 kilogram hypotenuse have to be at the same gravitational potential energy? So, again, we're going to use the potential energy here that we calculated in the last one of 7.8 times 10 to the 2 joules. Okay, we're going to use the mass of 3,000 kilograms. Okay, and we are looking for the height. Okay, again, don't forget, we have our variable of 9.81 meters per second squared. Now, we look at our formula, mgh. We're looking for our height this time, so we're going to divide both sides by mg. Okay, these cancel. Now we have Eg over mg is equal to our height. Now we plug it in and solve. So we do the 7.8 times 10 to the 2 joules divided by 3,000 times 9.81 meters per second squared for our height. And now the height is equal to 0.0265 meters. Okay, now we have 2 significant digits again, so we'd see 0.027 meters is equal to our height. Okay, so again, you're talking about a very small height for that hippo to jump. Okay, feeling okay? Ready for another one? Let's try another one. Okay, so this is talking a little bit more about how gravitational potential energy is relative. Okay, so we have to take a look at, we have a 500 sheet package of paper. It has a gravitational potential energy of 22 joules on the shelf relative to the desk. So shelf relative to the desk. Okay, what is the mass of the paper? So in the question, we are given our Eg of 22 joules. And we can tell that it's our energy term because of the joules at the very end of it. Okay, now we know our G value, 9.81 meters per second squared, and we know a height from the diagram. Okay, so in order to find the height from the shelf to the desk, we have to take a look at how high the shelf is, which is 140, and we have to subtract it from how high the desk is. So to find this, it would be 140 minus 70 gives us a total height of 70 centimeters. Okay? Okay, which is equal to 0.70 meters. Okay? So, we're ready to go now. Now we are looking for our mass. Okay, so we have Eg is equal to the mass of that times gravitational constant times the height. So now we're moving the gravitational constant and the height over. Okay, so now we're seeing m is equal to Eg divided by GH. So now we plug in and solve from our variables on the side. Okay, so we see 22 joules divided by 9.81 meters per second squared times 0.70 meters to give us a total of 3.2 kilograms. Okay, because remember, the reason why it's kilograms is our joules unit is equal to kilograms times meters squared per second squared. So that's where the kilograms is coming from. Okay, so we see this with all of our significant digits all wrapped up in a pile. So make sure you're taking a look at what you're relative to. So take a few seconds, write down 4 or 5 key points from the video and bring them to class tomorrow. Okay, well, again, we'll be practicing a lot more of this, so good luck. We'll see you tomorrow.